Alright, welcome back to the last discussion. So this is on 6.8, which is the applications of logarithmic functions. This is all the stories that have to do with the logs, the Richter scale, the population growth, all that. So in this video I'm going to end up doing 4 of the 6 homework questions. Try them before you watch me do them, because you'll get more out of it if you try to work through it rather than just watching me do it, because I can do this. Nobody cares if I can do it. What we want is for you to be able to do it, right? So let's dive into it. I'm going to do number 3 to start. So this is 6.8, number 3. And it says, we have the Richter scale formula, our simplified Richter scale, which is the log of what, x over 0.001, I think. Yeah. Find the displacement measured on a seismometer 100 kilometers from the epicenter of an earthquake of magnitude 6.7. So what I know, and a lot of that wording is just to qualify the use of this equation. The fact that the seismometer is 100 kilometers from the epicenter of an earthquake, none of that really matters other than to say this equation is now valid, because that's what this equation requires. But we have a magnitude 6.7. Right? That's the m of x. So a 6.7 is equal to this log of x over 0.001. I'm trying to figure out what x is, and x is the shake of the needle in millimeters of a seismometer, 100 kilometers, blah, blah, blah. That's what that is. That's the shake, right? So I'm going to rewrite this. The log doesn't have a base written, so it's 10 raised to the 6.7 is equal to x over 0.001. You can take 10 and raise it to the 6.7 and get some ridiculously big number. But instead, I'm going to multiply both sides by 10 to the 3, because this is 10 to the negative 3, right? And so if I multiply 10 to the 3, and I have a 10 to the negative 3, if I rewrite this just visually, that 0.001 is 10 to the negative 3. So I'm sorry. So I want that to be a negative 3. Multiply both sides by 10 to the negative 3. Then the 10 to the negative 3 cancels out with the 10 to the negative 3, and then the 10 to the negative 3 simply subtracts from my 6.7, so I then have 10 to the 3.7, which is a much more manageable number, right? If I throw that into the calculator, I get .5011 point some stuff, 87 something something. And they want this answer rounded to the nearest millimeter, so I would round that up to 5,012. And that would be my answer. Which is a lot, right? That's 5 meters, that's like 30 feet. That's terrifying, probably, I don't know. Good. Let's look at the next one, number 4. And it's the same question, except now we're doing a 3.1 in magnitude. And you'll note that it's essentially the same problem, just with a 3.1 here. So it's 3.1 is my magnitude, so instead of taking 10 to the 6.7, it's now 10 to the 3.1, but I'm going to make all the same moves. I'm still going to multiply both sides by 10 to the negative 3, 10 to the negative 3, so instead of 10 to the 6.7 minus 3, it's now 10 to the 3.1 minus 3, well, that's 10 to the 0.1. Right? And that is not a lot. If I plug that one in, I get 1.258, blah, 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 bunch of stuff. We're still rounding to the nearest millimeter, so 1 millimeter. That big, right? Teeny. Good. All right, the next one, number 4, a lot of people don't like these problems because they get a little bit longer. I like these problems because I'm the kind of person that ended up teaching math, so I don't know. Let's take a look at it though. We have a population of pink flamingos. They start at 750 and grows to 1,000 in 4 years. Okay. And then there's a follow-up question here, find the growth rate R, find how long the population reaches 2,000. We'll get to that in a second. The first thing I want to do is figure out what R is. And again, we're using this population as a function of time is equal to the initial population times e to that R times t. So what is R? Well, I know that at some time in the future I'm going to end up with 1,000 flamingos if I started with 750. And I know that it took 4 years for that increase to happen. So I can solve for R in this equation. If I divide both sides by 750, this ends up being a, what, 1.333 forever repeating. I'm going to write it, maybe as, yeah, I'm just going to write it as 4/3. This 1,000 over 750 simplifies down to 4/3 or 1.333 if you're in a calculator. But I want to rewrite this as a log, so this becomes the natural log of 4/3 is equal to 4R, and then divide each side by 4. So I have the natural log of 4/3. You have to be careful in your calculator. Maybe just do the 1.333 and write 7 3s or whatever you can. Take the natural log of that and then divide the result by 4. But in any case, I end up with R is approximately I get 0.07 19205 and some yada yada more digits, right? Somewhere around there. And so in the possible answers, they have 0.0719. That's the one that I would select. Click that button. All right, now that I know this, I don't need this work anymore. I do need the space so that I can find the next question, the number of years before the population reaches 2,000. When will there be, I don't know what I'm writing here, 2,000. Right? So solve for t if my population at that point in time is 2,000. Well, that would be 2,000 in for p of t is equal to my initial population is still 750. E to the, I know what R is, I'm going to use 0.071, they round it down at 719, and then I just have to figure out what T is. So I divide each side here by 750, 750, this is going to be forever repeating as well, it's going to be what, 2.666 forever? Equals e to the 0.0719t. And then I just have to solve for t, so I'm going to take the natural log of each side. or rewrite it as a natural log, that is. And then divide each side by the 0.0719. Okay. Divided by 0.0719. This gives me about 13.6 years. So it's also asking us here to round to the nearest, well it has 13.6, right? So the nearest decimal, whatnot. That's the best answer that they have listed there, so it's around 13.6 years, right? 13 years, 6.5 months, whatever that is. Right. All right. Good. That was number 5. All right. Let's look at the last one. Let's look at number 6. 6 is a radioactive decay question, but it's very similar to this in the way you would solve it. 6 just doesn't kind of walk you through it like that last question did. It asks you this secondary question, but you have to do all of that first work to find R first. So it says we have plutonium-241 has a half-life of 14.4 years. Am I writing above my screen? Yep, a little bit. Okay, better. And we want to find the approximate time required for a sample to decay to 10%. We don't know how much is there. It doesn't matter how much is there, right? If it does matter to you, throw in a number, right? 1. There's 1 pound of it. 10% is still 10%. So the first thing I want to do though is find R, because that's what I need in order to use that equation, and I use that half-life in order to find R, because if I have half of what I started with, that is 1/2 of my original amount. And that then is equal to the amount that I started with, multiplied by E times R times the T that it took to get there, which is 14.4. Again, this is why it doesn't matter how much we started with, because that amount cancels out. I end up with just a 1/2 is E to the 14.4 R. I'm just rewriting this as the coefficient in front. Then I just rewrite this as a natural log. So the natural log of 1/2 is equal to 14.4 R. Divide each side by 14.4. Then I just take this calculation, the natural log of 1/2, which is like negative 0.693, and divide that by 14.4. Whatever that ends up being, it is negative, and it should be negative because it's decay. I have negative 0.048. (1.3) or 1.4 if I rounded there. And use a bunch, use 4 or 5. It makes the calculation less prone to rounding errors in the end. But I found my R. Now that I found my R, I can do the other part of this calculation. I'm going to get rid of this, just so I have the space. How long does it take until I end up with 10%? Well, 10% is 0.10, 10% of the original amount that I started with. That's the P of t. That's equal to my original times e to the r, which I now know is negative 0.04814 multiplied by that time. Again, I don't care how much I started with, 10% still ends up just being 10%, 0.1. Rewrite this as a natural log. I get natural log of 0.1 is equal to negative 0.04814t, and then divide each side by negative 0.04814. That isolates the t on the right hand side, and then the calculation here, the natural log of 0.1 here I get about 47.8, it looks like. 47.83, yada yada yada. We're rounding to the nearest. Oh, well, there's just buttons that are all rounded to the nearest year. So 48 is an option. That's the one you would choose. All right, hopefully that was helpful. Again, this is the last discussion, it's the last section, so take your assessment, get ready for your final exam, and I'll see you guys. Actually, it's not the last discussion, because I'll do a final exam discussion, but it's the last section in the book, so anyway, I will see you guys for the final review.